Hello! Today I'll be talking about exactly what the video is titled, horsepower, torque, and ratios. I'll be discussing how they're related, how they affect one another, power to weight ratios, and how physics plays a role in all of it. First, I'll just show you every vehicle and bike I have in possession, since there's a wide variety in my household that allows me a good grasp on all of this. I'll just show some pictures of each of them as I introduce them, and when I get into the meat potatoes of this, I'll just roll some short footage I took of each of the vehicles and bikes just so you have something pretty to look at. First up, I'll start with the cars that are directly mine. My 2009 Hyundai Accent, the 4-door model, whose name is Gumball. My 1998 Mitsubishi Eclipse GS, whose name is Juan, as depicted by my license plate. Clever, I know. And me, my father's 1999 Chevrolet Tahoe 4x4, who my family very appropriately named the Hope. Note that these are just the vehicles that are mine and that I maintain. I'll be getting to the bikes shortly. Onto the cars that aren't mine. This is my father's company vehicle, a 2016 Nissan Rogue, who he deemed John Wick because of the plate. Next we have my mom's car, a 2007 Buick Lucerne, who she calls Lucy. Then we have my older sister's SUV, a 2016 Hyundai Tucson named Tuck. We originally wanted to call him Toots, but my sister didn't like that. And finally we have what used to be my younger sister's SUV and is now a family vehicle, a 1999 Honda CR-V named Yolanda, only because it's one of the two names that we could think of that actually rhyme with Honda. If you can't tell already, we're kind of a goofy family that likes to name all of our vehicles and give them personalities. Now on to the bikes. There's two dirt bikes and my motorcycle. My motorcycle, Winston, is a vintage 1987 Honda XL 250R that I enjoy cruising around on and have been slowly restoring to its former beauty, although it still rides like a dream. Then we have the dirt bikes that me and my father race competitively. Mine is a 2004 Gas EC 200 two-stroke named Chappie, after my favorite movie. And as you can see, it's a little big for someone who was only blessed with a height of 5'3", but I've gotten used to it and managed to make it work. And finally, my father has a 2005 KTM MXC 300 two-stroke. Before getting into some stats about each of these machines, let's just define some terms and what they mean in physics. Torque is a measure of force that can cause an object to rotate about an axis, or easier put, in a circular direction. This would be the engine rotating. With regards to the mechanics of a vehicle, it can be simply defined as the amount of turning power a vehicle has. The torque specifications that are given on a vehicle is the maximum amount of torque of the internal combustion engine. Torque can either be static or dynamic, and in this video I'll be referring to dynamic torque because dynamic torque produces angular acceleration of the wheels along the road or track. Horsepower could be described as the result of torque, as torque is used in the equation of calculating horsepower. It is a measure of actual work being done and how fast it is being done, or at the rate it is being done. This is why people love to boast about the horsepower their engine has, since this is a measurement of the power the engine produces. Okay, now that we're familiar with the terms I'll be using and the names of all the vehicles I'll be referring to, let's compare them and see how they rank on different scales. I'll show the stats I collected on each vehicle as the footage rolls, since I'll be referring to these numbers in this section. I first wanted to compare them in horsepower versus torque, since these are popular numbers people consider when purchasing a vehicle. Whether for daily driving, hauling, or for fun, most people consider how much horsepower and torque a vehicle has to decide if it's suited for their needs or not. As you can see from this graph I made, both my cars rank the lowest on this scale. But I'll be getting to why this graph doesn't define how sporty or fast and fun a vehicle can be in a while. Gumball, being the lowest on this scale, has only 110 horsepower and 106 foot-pounds of torque. Then, not far behind, is Juan with 140 horsepower and 130 foot-pounds of torque. Yolanda has 146 horsepower and 133 foot-pounds of torque, ranking very closely on this scale to Juan. Then we have Tuck with 164 horsepower and 151 foot-pounds of torque. Just above this is John Wick with 170 horsepower and 175 foot-pounds of torque. which my family finds kind of a funny coincidence considering my dad's race number is 175. But anyways. Next we have Lucy, sporting a pretty impressive 197 horsepower and 227 foot-pounds of torque, which isn't bad for a brand that has a rep of making cars for old farts. At the highest is the Ho, boasting 255 horsepower and 330 foot-pounds of torque. This scale shows how torque and horsepower have a pretty direct relationship. As torque increases, horsepower increases. On the other hand, when it comes to motorcycles and dirt bikes, they aren't typically sold by how much horsepower or torque they produce. These are sold by how many cc's they have, or, for those unfamiliar, cubic centimeters. This is a measure of how much engine displacement they have. The reason cars, trucks, and SUVs aren't ranked in cc's is because they produce a lot more than dirt bikes and motorcycles. And with bikes and motorcycles having much smaller engines with typically 1, maybe 2 cylinders, it makes more sense to rank them as such. cc's and horsepower are related, but only by a general correlation. Just like the previous table, this one also shows the direct relationship of horsepower and torque, although on a much smaller scale. First we have Winston, who has 20.2 horsepower and 14.6 foot-pounds of torque. Then we have Chappie with 38 horsepower and 23.6 foot-pounds of torque. The MXC 300 has 51 horsepower and 35.7 foot-pounds of torque. Note that I had to calculate how much torque the KTM produced since I couldn't find it online. For those curious, to find torque in foot-pounds, you take the horsepower and multiply it by 5,252, and then divide it by the revolutions per minute. The reason it's 5,252 is because this is the point at which horsepower and torque finally cross when graphed. This is where things start to get interesting, and when the physics behind vehicles becomes more apparent. Comparing how much horsepower a vehicle or bike has to their weight gives a good idea of how much work it takes to move the machine and how long it takes it. Now keep in mind that the higher the number, the better performance it has. Power to weight ratios are calculated by dividing total horsepower to their curb weight, which is per 10 pounds. Seeing this infographic I created, you can see that Lucy has the best power to weight ratio out of all the vehicles, with 0.051 horsepower per 10 pounds, despite being the second heaviest out of all the vehicles at her house. All of these vehicles are pretty proportional in their power to weight ratios, but their 0 miles per hour to 60 miles per hour times vary. The Ho is proportional, but with the best 0 to 60 time. This is mostly due to the amount of torque she has, since she was engineered to be able to haul heavy loads, like how she can haul our 12-foot trailer packed with anywhere between 2 to 4 dirt bikes with ease. 0 to 60 times depend on the physics of gear ratios, aerodynamics, and their center of gravity. For instance, although Gumball has a faster 0 to 60 time than Juan, his gears are short, meaning they're physically short and have close ratios, while Juan's are the exact opposite, with tall gears and spread ratios. What this results in is Gumball having a max speed of 110 miles per hour, while Juan has a max speed of 155 miles per hour. Juan will start to catch up to Gumball around 80 miles an hour and then pull away, as this is where he starts to hit his peak of torque. Juan also has a center of gravity closer to the earth, as he sits much lower to the ground with about 5 inches of ground clearance versus Gumball's 8, and an overall height of about 11 inches shorter than Gumball. Juan is also engineered with aerodynamics in mind, sporting a spoiler, short height and ground clearance, and a gradually sloping hood to cut through the air better. On top of this, he was also designed with stiffer suspension made for cornering, meaning that although Gumball has a better 0 to 60 time, Juan would beat him in tight loops and in corners without risk of tipping or losing traction. This is part of what classifies the Eclipse as a sports car, although on the surface there are people that wouldn't believe with lower end horsepower and torque that it wouldn't be capable of what it is. Where it all starts to click is when we take a look at the bikes. As you can see, bikes have a much larger power to weight ratio, granting them better performance. Although they produce much less horsepower than a vehicle, they weigh exponentially less. Even with a 33-year-old bike that has low cc's compared to other types of motorcycles like crotch rockets, Winston is able to quickly pull lengths on cars. With this greater power to weight ratio, this gives riders the ability to do really cool stuff. Cool stuff like this. Hopefully with this video you now have a greater insight into horsepower, torque, how they affect each other, and some of the physics behind them. I also hope this provides a better understanding as to why power to weight ratios are important to consider, and how horsepower and torque aren't the only things that determine the sportiness or performance in a vehicle or bike. Thanks for watching!